Welcome to GEO PSI's facility located in Northeast Calgary. We've put together actually a studio event where we're doing a number of topics with industry professionals and experts on various things, various topics associated with the use of pressure, temperature, acoustic data, micro-seismic data. We like sponsoring these events because it gives some education to folks that are using data, whether they be reservoir engineers, geologists, people who are doing well stimulation, completions. Data has some importance and some value, and it's better to hear that importance and value from a leading expert like Richard Baker. My name is Tim Kahn, and I'm your host for today's session. And welcome, Richard.
Yeah, it's great to be here, and let's have some fun. I think people will find this interesting.
Rather than everyone believe me that you're an industry expert, I have to put a little bit of bio in here of you, Richard, and I have shortened it greatly because we could go on for quite a while on the things you've done in the industry. So Richard Baker is a reservoir engineer, 40 years of practical experience in reservoir engineering, simulation, EOR, thermal projects. He has worked in a number of reservoir characterization, simulation projects, 53 countries. Wow, I'll have to add up how many countries I've been to. That's a pretty large number. He's held senior reservoir engineering positions in Shale and Husky, 2 bachelor's degrees, a master's degree in petroleum engineering from U of C, and a distinguished author, as well as receiving awards from the SPE and a CIM Service Award. You've twice won the SP Reservoir Characterization Award for Canada and nominated for the World Reservoir Characterization Award. In addition to authoring and co-authoring 60 plus technical papers, Richard is still teaching as an adjunct professor at the University of Calgary, and he sits on the Faculty of Engineering on their advisory board, and he's more recently worked on developing 4th year design capstone courses for U of C. And as I said earlier, Richard, we could go on, but in the interest of time, I just wanted to, thank you for being here. And I should also say, in terms of housekeeping, we will have places within the presentation and at the end where you can ask questions to Richard based on the content he presents today. So I'll turn it over to you, Richard.
Okay. Well, it's a pleasure to be here. And what I want to talk about is sort of practical injection surveillance for shale plays. I've been lucky. I've been involved in naturally fractured reservoirs for a long time, almost 40 years, okay? And I think when you start off, you think of quite simple systems. You learn by simple systems. So I would have started off 40 years ago with sugar cube models. And I want to show you now the difference between, hopefully, a practical application and how to develop your mental models, because it's extremely important on how you economically optimize shale plays or lower permeability reservoirs. In this session today, we're going to talk primarily about tight oil and gas, or tight dry gas, okay? I'm going to talk a lot about fracture architecture, and we're also going to get in your mind, think of fracture architecture like a cloud, okay? But also think of fracture connectivity like highways, right? Because that's going to be very important. So we're going to talk about that primarily today. Obviously, something like this could take days if you wanted it, but I want to keep it light. And so that's going to be the focus of our discussion today. So I want to start off with some of the major challenges and questions associated with horizontal multifracs. Obviously, we've seen rapid growth in the last 20 years in this field, and it's still a hot area of interest, okay? And next to, let's say, oil sands in Canada, this is by far the most prolific sort of area. But what you need to understand is what you don't understand, okay? And that is, when we look at well spacing and fracture design, proppant, number of stages, staging, spacing of those stages, fracture height growth, and fracture hits, we're in a way, we're trying to evoke a mental model in this thing. And that what I want you to do is also focus on the lower right-hand picture. That's just an outcrop. You could imagine that if I start introducing stresses and strains or fractures into that thing, the natural fracture system is going to have a strong influence on the induced fractures. So I think what happened 20 years ago is we assumed, okay, we know what our pressures are and our proppants are, and this is how it really works in an ideal world. The trouble was, even 20 years ago, I'm embarrassed to some of the models that I even put together, they were too simplistic. Even though I'd worked 40 years and worked for the DOE of the United States and worked all over the world in naturally fractured system, even the models that I put in were too simplistic. And that's a common phenomenon. It's similar to how we approached COVID initially and how we approach it later on. So what happens is you need to understand the fracture architecture. And in order to do, the reason we're more concerned about that is that now we see fracture hits, okay? So fracture hits are obviously communication during hydraulic fracturing. Obviously a safety concern as well as an economics. We'll talk about how that influences spacing in a second. But we also need to understand what the fracture permeability is. Okay, are they wide fractures or are they narrow? Do they have a lot of pressure drop associated? And also probably the most important, which has changed in the last 15 years, is the stress effects, okay? So it's not enough for me to have a perfect image of a frac job with microseismic. I need to understand how that fracture cloud changes with time. And I also need to know where are the highways through it, because a cloud is one thing, but fracture hydraulic connectivity is quite another. And then related to this, just show you how big this topic is, well, do I go 2,000? Do I go 3,000? Do I go 10,000, right? So I'm going to show you some examples of some tests in West Texas in this case. But when you think about it all, it relies on the architecture of the system. And that architecture of the system is largely controlled by by natural fracture systems. So yes, you can induce stress on that image that I have below on the right-hand corner, but you can see how it's going to grow depending on where those natural fractures are.
So given that these effects are so complex and there's many variables and lots of heterogeneity, where does pressure data actually help us determine these things?
Pressure data is absolutely critical in my mind. If you look at even the work that I did 30 years ago for the DOE and for Pioneer and whatever, what we found was that pressure data was really, really important on understanding hydraulic connectivity. So if there's one thing that you leave this presentation with, I hope you get the feeling that pressure data is one of the absolute key inputs into what your fracture architecture is, and think of those highways, okay? So if I was gonna drive from one city to the next city, and I said to you, well, let's say Edmonton to Calgary or Calgary to Edmonton, right? And I said, well, I travel at 3 hours. Which highway did I predominantly go on? You're gonna say highway number 2 as your default. If I told you now that I'm gonna look at, you've had 12 hours of travel time and you got to Edmonton or 12 hours later, well then there's a lot of secondary highways I can do. And so think of the microseismic as sort of giving me the cloud of possible fractures, but what you really want to know is what are the best connected fractures and how do they affect your drainage patterns.
Interesting, thank you.
So I want to stress this time and time again, because I think when we look at fractured systems, initially we start off with quite a simple model. And so think of like your sugar cubes in your box, you buy it at a grocery store. I mean, that was my initial view of fractures 40 years ago. What has happened in the meantime is acoustics and obviously seismic have given us a real feel of the complexity of the fracture system. But again, you need pressure data to understand the permeability of the fracture system, because just geometry alone doesn't necessarily allow you. Now, if you look at the figure here on the right, It shows a pretty famous fracture job done in the Barnett. And it has an observation well. It's intersected various well bores, and in this case, it's a vertical fracture. And you can see these microseismic events. And what you need to understand is you can get 100 or 1,000 microseismic events. So it doesn't necessarily, it tells you kind of a cloud of what's happening, but those don't necessarily mean their connection during production or even, whenever you do the job. So again, think of the cloud of points and the microseismic as like a balloon or like a shape factor, and that is great because it's given us a lot. It's basically shown that our old model of fracture, single fracture, perfect half-length type of behavior is wrong. Right. But what the pressure data does, and it's either through production data analysis, like production data, or transient, or just interference between wells, you can see that my complexity is much greater. So if I take that image in the on the northeast, the right side of the diagram, what I can also tell with my wells that have intersected is how much pressure response I see. Now the beauty of what we see now is that our resolution is so much better. Now you're not just looking at single points some distance away, you're looking at, with fiber, you're looking at much better resolution than you can possibly get. Okay, so I wanted to sort of just take it back for a second, okay? And we're gonna use this example again and again and again, and it's an idealized example. I mean, I can show you real ones, but some are confidential. Now there's two things to remember in this talk, okay? One is that your fracture systems are very complex. Actually, let's say there's three. And then next is that the pressure data tells you where the highways are. And the third thing to remember is only about 1% of your fractures actually hydraulic connected. So you can have perfect fracture counts from, let's say, image logs in horizontal wells, but that doesn't necessarily mean that all of those fractures are open. Only about 1%. So what's important is, let's say during production, is how much interference do I see in that well pair? Now, I would be embarrassed to tell you, even 10, 15 years ago, we would have done simulation. We've had equal fracs. Well, the problem with that is, go back to that image of the shales, is that isn't likely to be reality. And we definitely see that when we look at acoustic type data. So the advantage of the pressure data here is that I can measure the pressure at the parent well and the child well and get an idea of what that differential pressure is. So if I have a number of well or a number of pressure points or even a continuous type more thing, it allows me more and more resolution. So think of those pressure measurement type of devices and think of them as ways that it tells you the geometry of the hydraulically connected fractures. That's really, really important. And so one of the things that is the biggest single issue when you look at shales and when you're looking at well spacing is, yes, we see fracture hits, but are they still connected when I draw down the pressure? And I'll talk a little bit about that later. So that's really one of the real key learnings you get from it. So think of those points, the red dots on this thing, it's almost like pixel resolution. If I want to make a picture of a rose, I need so many pixels to do it. Now, we're going to introduce a concept here that I think is really, really important. And of course, I'm going to make a generalization about things, and I'm going to assume the other variables are constant. So I'm going to assume that, let's say, the permeability of the shale itself is relatively constant when I do this. One of the biggest important factors that we've seen over the last 10 years is just what kind of well spacing, okay? So it's one thing to put a well, and then a kilometer away, you see another well, and you say, well, that well did good, and we'll drill another one. And so what you've seen is there's gone to more and more tighter spacing in with these wells, which is easy to optimize when you're at a kilometer away, but when you get closer, then you start to see an interference effect. So if you look at it just on very simplistic economic terms, so if I look at net present value, let's say, and then I could do this thing as payout or whatever variable I decide to use, or is if I have spacing. So if you see this graph here, I've got wider spacing. Let's say that's at 300 meters, and then I go down to 150 meters, and then I go to 150 or to 50 something. And you think about it, there's an economic optimum. And that economic optimum is where I get the most bang for my buck for the wells, right?
Yeah.
So if you're far on the right-hand side of that diagram, you're going to leave reserves at the end of the day. So if I was at a kilometer away, I'm going to leave reserves at the end of the day. On the other hand, depending on what the fracture network looks like, I can get 2 well spacing, and then I can see just straight interference between the two. And so I really wanted to stress is, think of this diagram, and obviously this is just a generalization. It's going to vary from play to play. And then we're gonna here, if we're on the far right hand side, we're gonna have a high pressure resource at the end, or when the well is being abandoned, or you're gonna have a tail that goes forever,
right.
On production tail that goes on another. If you space that thing very closely, your wells closely, then what happens is you have overcapitalization. So let's work back to the physical model now. It's a question of how many hydraulically connected fractures there are and at what spacing there are. And in that case, obviously, micro-seismic is great, and as well as pressure measurement data.
So this notion of overcapitalization to me means, okay, we're out there, we're doing multi-stage fracs, we're hitting these shale reservoirs with a big hammer.
Yeah.
So maybe there's an opportunity to hit it with a smaller hammer and reduce our lateral lengths and the number of stages, but how do we know how to get there? Maybe that is by having more surveillance. So we have more spatial, more temporal data to help us understand we don't need to be hitting these wells with as much capital, as much fracs, et cetera. So that's what it means to me. And so overcapitalization to you means, from a reservoir perspective?
Yeah, it's basically that you have almost too much interference between wells. And in a case of a shale play, it's that you have a hydraulic, like you can control how many fracs you put in the ground, but you can't necessarily control on how efficient those fracs are, and you can't control on which parts of the reservoir they drain. So you want some interference between the wells, but not so much that you've drilled a well that's totally redundant.
Right.
And so overcapitalization is basically pretty common problem. And it you can understand, people get very enthusiastic about the initial wells, and then they infill drill them, and they may still get results. But there gets to be a point where you overdo it, right?
Right.
And too many plugs into the bathtub or drainage points.
Yeah, interesting.
So this really becomes a real key issue when you come to whether I should infill drill or not. Now, what I wanted to show you here is I've take a mental model, and I think for some of you guys who are a little younger, which is probably all of you guys, is that I think it's important to build your mental model. I think the problem that we have is we rely on simplistic models. And when we rely on simplistic models, it often gets us in trouble when the real world hits us with complexity. So what I showed you is a case there where I have an optimum net present value at about 150 meters. What I really want to know is, what does that look like from a fracture point of view? Now, if we had perfect knowledge of where the fractures were, and a priori, you wouldn't need to do that, right? If your models were already at ladder. That extensive, but usually that's not even close to the case. And the trouble is the less you know, the more it seems simple, and that's how we learn. There's nothing wrong with starting with simple models. It's just, how does the data complexify?
So looking at this,
Yep.
So to kind of distill it down,
Okay.
for the neophyte like me in the room, so what sort of data do we need, and what type of data to support this supposition, if you will. Like, what data should I, if I had all the money in the world and I needed data to support this,
Right.
what data sets would you prefer as a reservoir engineer?
The microseismic is key because you want to know what that shape of the cloud is. So, but the pressure data is also key in that when I look at this, I can see that there's direct connections along there. So hydraulic or pressure data tells me a lot about how effective that fracture is draining, and also is it connected to the next well. Obviously, it's connected to the next well. I've overdone it now. But if I just have, let's say, one connection between those two wells, and I didn't know the shape of the cloud, I also don't know how well I'm draining other portions of that reservoirs. So there's where the whole concept of secondary fracture systems come in, and that's a whole different topic.
That's a whole other, yeah.
Yeah. But if I look at it, if you look at the type of connectivity you want enough connectivity that you're not leaving reserves under, and so generally what you want in an ideal world is all these equal fractures, which never really happen, but all these equal fractures. And then that they're almost at the point of interference, and there may be a little bit of matrix permeability between it, and that gives you your economic optimum. If you go to the third case, where there's indirect communication, but the matrix is extremely low, then you have high pressure and abandonment at the end of the whole thing.
Right, which is not optimum.
Yes, which is not optimal.
Yeah.
Okay, so you can see, I hope I've given you a mental model to understand how that fracture length controls the spacing. Now, there's other factors that affect it, but I always think of outcrops, okay? Because outcrops, for me, give me a feel of what is going on. It's my analogy of what's going on. And this is an excellent outcrop. And it shows, you can see, it's clearly see the fracture zones and the corridors. And so imagine fractures coming out where those big fracture breccia is and coming out on towards you on the beach. Obviously that controls your fracture spacing with that. And so when you get to economics and all that kind of thing, you have to be aware of what those spacings are.
I was going to ask you a question. Why do we need pressure data? But I think you've covered it very well so far.
Well, the only thing I'll add is it's not just do I see a hit here or a pressure withdrawal point. It also, even in the build-up period, it helps me tell what the matrix permeability, and that's a very, very important issue, because if you look at where your optimum is, it depends strongly on that, on what the matrix permeability is as well.
Very good.
So what I wanted to show you here was just kind of, now I know this is giving you a lot of information in a graph form, but you can see here, as I change my fracture architecture, so if you look at the initial one we talked to was the black line, and then we talked to the red line. The red line is where I may have a lot of short fracture system, and then over on the other red line onto the right here, that's where you have longer fracture systems. So you can easily convince yourself that if you have long hydraulic fractures, you shouldn't be narrowing your wells in too much, because there's too much of a risk associated with that.
Like of interference.
Interference effects, yes, pressure interference, right. And how pressure, what's also important is how pressure interference occurs through time.
Right.
Okay?
Very good.
One of the things that I think, if I could go back 40 years and slap myself for it, was initially I started off with Husky, and we were doing interference tests, and we were looking at fractures, and these were injection-induced fractures. And I had a very naive concept. I thought, well, if I see this between this well and this well, or if I don't see it, I think those are effective fractures. So I'd take, let's say in this case, we were 200 meters or 400 meters distance between wells. Now, what I would have told myself 40 years ago is that not all your fracture lengths are effective. So what people typically do is they do a volume calculation. They go, oh, my fracture's this height, this width, and this long, and therefore, and then I put so much proppant in here, this should all be open. Well, that isn't really the case, okay? And so what you see when you look at fracture, like pressure transient test or even rate transient analysis on wells, is that only about 20% of your fracture length is effective in a lot of cases. And that's due to like multi-phase flow. It's also due to cleanup, and then it's where you put the proppant. So we initially induce a hydraulic fracture. So you see a fracture hit, but you don't necessarily know, is that connected, and would it be connected during pressure? Because remember, we're well above frac pressure, and now we're going to draw that same well down, at least on primary, and we're going to do it at a much lower pressure. So those fractures are going to breathe and close, right? That's one of the things I learned from geomechanics.
Where I met you, yes.
Yeah. I think that's it.
You learned that from
all
me,
you.
yes. Yeah.
Okay, but the next important things is where the proppant is, okay? So again, you're at still relatively high pressures, and you're going to place that proppant. But just think about how sand would settle in a glass. Think of also how sand will settle in your frac job. So fracture proppant isn't a given either, right? And then finally, you get down to what the effective fracture length is. So you can see there's been numerous studies done on comparing by really, knowledgeable people, showing that the difference between effective fracture length and what you initially think is totally. And that's exactly what we saw with Pioneer and the DOE from the US on when we were looking at the Upper Sprayberry in what you would call, they're lower right now in the Wolfcamp and that kind of stuff. Mm-hmm. But that's exactly what we saw effective length not equal to necessarily hydraulic fracture length. One of the things that I said that you need to remember from this presentation is that not all fractures are continuous, okay? So imagine that you had a set of matches or toothpicks is probably a better way, and you throw it on the floor. Well, what you'd find is if you look at that connectivity of those fracture systems, it's not as big as you want. In fact, if you look at it on a 2D sense, what you'd see is only a small percentage of fractures. Now we know this from nuclear waste disposal, we know this from tracer studies, and we know this from just looking at outcrops and whatever. So we know these numbers are approximately correct. So when people say to me, oh, well, I have an FMI log or I have a horizontal core from that well, and I count 100 fractures, immediately in my back of my mind is, but which ones are connected? Not all of them are gonna, it's like you saying, I'm gonna leave the city and there's, at the outskirts, there's 100 exit points on it.
Right.
The real ones are what are connected to Edmonton or what is connected to the big highways.
So things like distributed temperature data gives you a real spatial awareness of where these fractures are open and where they're closed, right?
Exactly. And that's where where I think, and give a real credit to Mark Zobek and some of the people, that Colleen and all that. What I found so interesting is when you and I got together, when we started looking at the results, even though I didn't even know who Mark was and he didn't know who I was, and all that GMI stuff, you came at a problem totally different than us. You came at it like my second degree out from mechanical engineering, where I came out as basically petroleum engineering and observing fields, and yet our answers were very similar. And this one I would totally agree. I mean, my experience is the reason why we have problems simulating naturally fractured reservoirs, even with or without hydraulic fractures, is that we don't contact this huge swath of the reservoir. And that has huge implications in things like geothermal fields and that kind of stuff.
What about carbon capture?
Well, it's the same problem that
Same
you're going to have with some. Now, it depends on the amount of fracturing you have,
Right.
and it depends on what radius you're looking at. I mean, it's quite complicated.
Right.
So, again, one of the things is important is again, we're going to go back to this parent-child well, and we're going to look at the time of hydraulic fracture. So obviously, you're going to see this connectivity during that period, because what you've done is think of going back to those fracture pictures, is you've connected one of those big highways, and you're going to notice it, right? But that doesn't necessarily mean that the connectivity is always high, right? Remember, it's really not a true single fracture. It's a cluster of fracture that really matters. So I can't stress enough why pressure data is important. I mean, if the reason we did the Sprayberry pilot in like West Texas and whatever was to try to get CO2 into those natural fracture systems and water. And there was definitely learnings about them. But I would say that pressure data was absolutely critical, as well as production data.
There's still a really good paper that Pioneer did on their use of pressure gauges in the Sprayberry for interference testing, et cetera. It's an old paper, but it's still very, very valid. You probably have read it.
Yeah. And if you look at what I think the majors have, and Pioneer also, I know they're Exxon now, but what they did is they took a systematic approach to it. So let's say you have one well every kilometer in a new shale play, and that well's a great flower. It's not hard to convince yourself that you're going to need to drill or another well. You're going to accelerate the process. Where the real finesse comes in is bringing multidiscipline teams and then looking at it holistically. So that's really, I mean, I can't claim for some of that work, but yes, Pioneer definitely did their homework, and they took a real scientific approach. And that's no different when you look at what Chevron or Exxon or whatever. It's very systematic, a lot of data intensity quite early. When you're navigating, it's like you're moving into a harbor, and there's maybe rocks on part of that harbor. You need the most information just before you enter the harbor. After you hit the rock, it doesn't do you that much.
It's really interesting to see how technology has brought a convergence of all the disciplines together in the same room. The reservoir guys never used to talk to the geophysicists. The geologists didn't talk to the drillers. Now you've got everybody in the room looking at all this data. It's an exciting time in the industry.
Well, and it's important to talk to the same types of image. So what I know about multidiscipline teams and about just in general reservoir characterization is that almost everybody has something to add to the picture. And you can easily convince yourself on the wrong, you can drink your own whiskey or whatever.
Yeah.
And I think that what's exciting about what we see with this is it's analogous to medicine. Okay, if you look at before the 1900s, our medicine was quite rudimentary. Okay, you had bloodletting, you had some real unknowns associated with it. But let's say between 1900 and 1920, the amount of medicine and our understanding of it went up greatly. And so this is analogous to what we see with hydraulic fractures in the shale. And so what's happened in medicine is you had the X-ray, you had understanding of how bacteria works and that this causes certain diseases, whatever. And in addition, you have pasteurization and that kind of stuff. So what you started to see was a holistic view of what the reservoir is going, or how the human body behaved. And the same thing is true when you look at the shale plays. And I give tremendous credit to some of the people who've been involved with this and the understanding of things. But like usually, the more measurements, the more data you have, the more complex the problems looks like. And it's easy to overgeneralize when you have limited data. And so, I can look back and beat myself up and say, why did I do that? But I also realize that data drives a lot of this stuff.
Sure.
And I want to emphasize that, your acoustics give you the cloud, but your pressure data gives you the highways in your interference tests. But it also gives you information on what the shale permeability might be itself. And I wanted to just show you an example. Okay, let's take a well, and let's say we'll make it fairly well instrumented. Okay, so we're going to take this parent well, and we're going to introduce a series of pressure measurements along there. And what we're going to do is we're going to then drill a child well, and we're going to create a hydraulic fracture. So what would that look like? Okay. Mm-hmm. Now remember, it's all fairly highly idealized, but you're going to have, let's say, a pressure hit associated with that. So you're going to see a high pressure above, obviously initial reservoir pressure, and you're going to see that on the parent well that you wouldn't have seen it before. Now you can see just by the nature of that signature that it's not necessarily like a long-term, because my fracs are only so long in time. So I'm going to see a rapid rise and then a rapid fall in that. Okay. Now, if I now start producing that child well, and I'm start to monitor at the parent well, I'm going to see a feature, okay? And I'm going to see if that, let's say that connection was open, so that I have a highway between the parent and the child well, I'm going to see a drawdown when that child well starts to produce, right? And that's telling me, you know what? There is these wells are becoming very similar, and especially when you start up the parent well again, then you're going to see a lot of interference effects or lack of interference. So if you saw a major interference effect at the parent, it's going to draw down the pressure and keep the pressure low for a while. And you're saying that highway effectively drains that drainage area, right? Now, it'd be important to look at the other pressure gauges along that I'll talk about. On the other hand, if you keep your parent, if your parent doesn't see much difference in pressure, then you're saying, well, that fracture is maybe open during hydraulic fracturing, but it doesn't open during the production phase. Remember, it's stress-dependent type phenomena. And so if I continue this on now, I start up my well. I'm going to start my parent well. My parent well's now on, and my child. And all I've done is I've taken this longer. Obviously, if my parent well and my child well have the same amount of drawdown at points A and B, then I've probably overcapitalized that well. Okay. On the other hand, if they're in two different pressure systems, then it'll be good, right? So this kind of practical data analysis is going to tell you more than all the theoretical models you put together. I mean, basically, I've spent 40 years in doing reservoir engineering, and you need to have theoretical models just to get an idea initially. But what's more important is how it behaves with the observation. So think about that Titanic. I'm moving close to that. I want to know generally where is the iceberg start, right? So I need a kind of a theoretical model to start. But when I start to see icebergs to water, I also need to react to that data and then change my strategy. So I might find that parent-child well pair has too much connectivity, but my next set of wells I won't, or even then I won't necessarily draw them down to the same extent.
So given my available budget, and not to seem self-serving here, but if I could put as many gauges in that horizontal well to understand those effects, I would be better off in understanding how I need to develop this reservoir.
Right.
If I say I have a gauge at the toe and the heel, that might not give me that spatial resolution to see the differences in between.
Exactly.
So, again, yes, available budget, but people need to understand that having more gauges, which again seems self-serving, is better in an exploration sense, in an early development sense.
It is self-serving, but it's just think how many pixels I need to get a picture of a rose, right? There's a certain amount of resolution. Now, you're not going to necessarily instrument every well the same way, but what happens is you get a learning from an area, and then you transpose that learning to other things. And so, I just think that in general, pressure gauges are kind of underutilized. I mean, I'm basically taking that in the context of 40 years.
Yeah.
So some of that's just legacy. Like, honestly, I think we would have, our strategy would have changed dramatically if we had some of the data people have today. And it's easily available data.
Sure. Thank you.
So the other thing I wanted to stress, and this is just like this geopractical type stuff. This is not rocket science. I'm not trying to derive a partial differential equation or whatever it is. One of the key things is also, okay, how long do I want to make these wells? Okay, and how long I want to keep these wells is going to be a function of the fracture architecture, but it's also a function of what the pressure drop is along the horizontal well. Now, what I've seen, and remember, so what I'm going to do is I'm going to say, okay, there's, let's say, 6 points here. And we're going to start off with the heel of the well, okay? And then we're going to look at, let's say, a second well and what its performance is. So what I'm going to do here is I'm looking at pressure point 1, pressure point 2 through time, and then as well as 6, which is at the toe of the well. Let's say I had this type of pressure profile. What it tells me is that 1 and 2, there's very little pressure drop associated with that. And then where you find 6 is I'm not even draining that toe very much, right? I'm backing off pressure. Flow is easily feeding in. Now, then it's the case is, well, why do I necessarily need that long well? But also, how does that change, evolve through time, right? That's a really important point.
So this effect doesn't really matter if it's in conventional heavy oil or a shale play or conventional oil play. Having that data along a lateral could help me determine how I need to develop the reservoir, how long those laterals should be, those sorts of things.
Yes, it's not unique to shale here. Right. In fact, I would say what has been a surprise when you look at, let's say, inflow control devices and whatever, a lot of times my expectation, I was wrong on this, was that, oh, it's more homogeneous. You're just draining the bathtub. You're putting more bathtub drainage points and that's it. But what you see is that each one of those points is a function, a pressure is a function of both the inflow performance as well as the pressure drop along that. And to get good drainage, it helps if you know what that system is.
So if I have too much of a pressure drop from the toe to the heel, that might tell me I maybe shouldn't have that long of a lateral.
Yeah, exactly.
X number, thousands of dollars per meter to drill that additional reservoir.
In fact, you see that in SAGD sometimes is people have shortened their wells just because of the amount of lack of drainage out of a thing. And the same thing goes with fractured or shale plays or natural fractured plays.
Well, and conventional heavy oil, the same type of thing?
Same thing. You just primary production.
Okay, thank you.
So if we go back to this kind of diagram, you can see, and this is a classic diagram. Everybody uses this one. It's way back from 2002. And again, it's the Barnett Shale. Is we get an idea of the cloud from the microseismic. And there is, without, if you looked at 1,000 microseismic images or 10,000, you're going to walk away and think that fractures are no longer these simple planar. Remember, 20 years ago, they're big, simple planar, go from equal wing length from the producer. That has been pretty well blown to crap on that.
So basically today, the distributed acoustic fibers are basically, there's this discussion where they're actually replacing what people are calling legacy geophone data because of that spatial resolution. Have you looked at the data differences between
no,
acoustics?
I mean, to be honest, I'm not qualified to be like a geophysicist, but what I would say is that we have a lot more granularity in our images, and we understand how stress and strain is affected in the reservoir, and that's not just in shale plays, that's universally. And so what happens is it's given us an opportunity to look into the reservoir where we've never been able to look before.
Right.
Now I want to show, I want to kind of keep this not too long here. I won't bore people together. But this is a pilot out of Midland, which I spent lots and lots of time in. And it's really what the ERTEC guys have done, and it's an excellent. What you basically have is the diagram on your left-hand side just shows you where we are relative in Texas, and you're obviously in the Midland Basin here. And what they've done is they drilled the Wolfcamp. So the stuff that I did, oh my goodness, 30 years ago in the Upper Spraberry, they're going now down to the Wolfcamp and deeper into the Dean and whatever. And what they did is they drilled 11 wells, okay? And these 11 wells are like 10,000 feet. So this, and they instrumented these to death, right? So this is a great case study, and it was done with a data intensity that's kind of hard to argue with. Mm-hmm. They did 400 hydraulic fractures, they did DFITs, image logs, you name it, geomechanical, pressure, tracers, post-treatment analysis, seismic. So this is a data-rich source, and what it allows me to do is talk to this data, and then I'm not worried about confidentiality issues. So anyways, very impressive. And then think of it also, because you're in the Wolfcamp, it's a bit of a wine rack. So you have wells on above and below, which I'll show you here in a second here. Now, this is a Wolfcamp again, and you can see the wine rack. If you look at the cross-sectional view at the very top, you can see the difference between those two sets of wells is about 325. And then the lateral distance, it looks like I have a spelling error. The lateral distance is about 660 feet between wells. And you can see in the bottom diagram, you're looking at downhole micro-seismicity. And what they've done is they've layered all those fractures. Remember, there's a large number of fractures associated. So it's a cloud. You can see there's the cloud for you. And there's a cloud. And you can see it's color coordinated so that different fracs have different colors. But obviously, with this number of fracs, it's pretty hard to see one event or whatever. Now, the interesting part of this is this experiment in the Wolfcamp and the Upper Wolfcamp is that you saw pretty good hydraulic communication during the frac jobs. But when you looked at pressure to communication 200 days later, then you don't see the same interference at that. And that's why those gauges are important. Yes, it's nice to know that there's fracture hits, but it's also nice to know what my when drawdown begins and how fast I should draw it down, just my behavior of the system. And I want to just illustrate this with one more. And I know, like what I've done in the diagram on the left-hand side is I show reservoir pressure versus permeability ratio. That's just initial reservoir pressure. Initial permeability, and then you see how it declines. And if you look at the dark line, we're looking at permeability. So you can see here, as I start drawing down from, let's say, this is a deep well, obviously. If I draw down from 7,000 to 6,000, I have dropped 50% just in that first drawdown, right? So what you often see is that you build a fracture network, you put proppant in it, and remember that proppant is like you're carrying water, carrying sand in a mixture, gel mixture. That closes, and then what happens is it continues to close. So if I now drop down to let's say 3,000 PSI, I have lost 90% of my productivity from that alone. That is a critical aspect because yes, you may have had great fracture connectivity at this, but it depends on what your abandonment conditions are and your fracture architecture.
Sure.
So I wanted to stress one more thing that we do with fractures and height growth, because I think it's an important point, especially when you're looking at wine racks, right? So if I go backwards and I can see that I have communication, if I look at the shale, if I look at the micro-seismic image, in the bottom of the left-hand side on this, I can clearly see there's lots and lots of continuous type rock associated during the hydraulic fracture, okay? And And this is example. This is from Don Lawton and Dave Eaton at the University of Calgary, and they show a Beaver Hill Lake pool, and you can see these seismic clouds, and they are great because it kind of tells us how much height growth we have. Because obviously, if I have a lot of fracture height growth in these things, I don't need the vertical spacing. Like I can widen my vertical spacing, I can narrow that or widen that line rack. And so the seismic events are very good for getting a handle on that, and you can see it. And here's where I'm going a little bit, it's still in the hydraulic fracture, I'm still in a shale place, I'm in the Barnett Shale here. And this is pioneer work that Warpinski and Fisher did, and this is excellent paper, whatever. But you can see here where they've mapped both the water leg at the top, so it's just measured depth, and then to the depth of the well, and you can see where you're looking at hundreds or thousands of hydraulic fractions, micro-seismic, and you can see here where there's not a danger that these hydraulic fractures are going to go up and frack your water column up, 8,000 feet away, right?
Right.
So it's.
But in a shale play that has high differential stress, like the Montney, there's a lot more potential issues there, correct?
Yeah.
A lot more fracturing.
Yeah, and also things like faults. As you would have learned in geomechanics, faults and some of this stuff change your fracture heights. In fact, if you look at the diagram again, the areas where I have higher height growth are generally associated with faulted areas. So yes, I mean, geomechanics and also geological features are critical. And it's important, I will talk about this later, perhaps in another conversation, but it's important from a CCS point of view or from a drainage point of view and just oil and gas production, just how big those fracture heights are.
Right, or an injection well.
Or an injection well.
Saltwater disposal well.
Right, yeah. Big issues associated with that. So I hope I've given you a feel of how acoustic data is necessary, and I think Tim brought it up well, was why spatial resolution is important. Because let's face it, the more pixels I have on that TV screen, the better resolution I can see on that rose. Right. I hope I've also given you a feel of why those pressure systems are important. Because although we can define the clouds are non-unique solutions too, is that they're affected by stresses and strains that may not mean there's proppant in those type of things, or that they're open under these conditions. So pressures are important, and so is acoustics. And if you want to run in blind, that's fine. It's similar to like going in with the Titanic. If you want to go in full speed into the ice fields, good luck. But it's not necessarily where I'd start from.
Yeah.
The next thing that I said that I hope you want to understand in this is the fracture systems are inherently complex, okay? We have shown you a number of outcrops, and you've seen the heterogeneity. And if you don't believe me, just go to anywhere in the world and look at an outcrop with some faulting or fracture. You're going to see complexity that's not easily described in one or two parameters. I think that's the problem that we did. I mean, we did the best we could with the legacy models that we had.
Sure.
But if you ask me now how I would approach those, it's like saying to somebody, okay, I'm now going to Newfoundland from London, and I'm going to go through the ice fields again. Are you going to slow a little bit? Yeah. I think the resolution of your data drives good models. Without good models, you're pretty well hooped.
Right.
So, to conclude this, I want to stress something here. Think of that now you're going to try to create a mental model, and that mental model drives a lot of your decisions. And so you're going to get that mental model, you're going to look at pressure data, you're going to look at acoustic data, and you're going to look at maybe things like temperature, and you're going to get an idea of what the connected fracture volume of that, okay? And so from that, you get an idea of the vertical placement, where that wine rack, where do I keep my wells, like in, let's say, a thick play like the Montney or something. You're going to get an idea of what the well spacing is. How close should I have those wells? And then you're going to get an idea, well, how effective was the number of stages in the proppant? And it's a learning, there's a lot of variables associated with it. Then I hope I've given you a feel of how that'll affect well length and how I might do that differently if I had a lot of pressure data. And also, the last thing it helps you to do is you understand that geology varies, okay? Just like those outcrops vary. And there's going to be interaction by faults and stress fields, a whole bunch of things in there. And I'm not saying you ever get a perfect understanding of that reservoir, but you get a much better, more practical understanding of what parameters are critical and what parameters aren't critical.
You know, my takeaway from this is, and it's an old expression, you don't know what you don't know.
Yes.
So, you know, the more information you have, be it pressure data, be it acoustics, etc., you know, you form on a hypothesis when you're developing a reservoir. Can I hone in on what I need to know to develop it in a more efficient, less costly manner, maybe with less wells, less stages, really take advantage of the reservoir I have. That's my takeaway with all of this, especially in shale plays. And
I think the thing that I've learned in 40 years is that what I've learned is you can have great engineers, great geologists, great everything, but if you lack data, your chances are still wrong. Remember, we sample about 1/10 billionth of the reservoir in general, okay? And so we need data to tell us what directions are. And so good engineering or geology or geophysics doesn't necessarily substitute for lack of data. If you have lack of data, it's easy to convince yourself you have a simple model when you simply don't have any data, right? That's the easiest thing in the world to do. And so I would totally agree with you, Tim, on that one. Okay, so I'm going to move on with some conclusions, and I think some just overall lessons. I first want to look at, one of my heroes is Neil deGrasse, and I would say what he said here is very, very true. One of the life's challenges is to know enough to think you're right, but also not enough to know when you're wrong, okay? And so getting enough knowledge to knowing when to laugh at yourself or when to understand your humility, that's really important. And you need data to do that, right? Mm-hmm. So when I look back, and it's always easy, hindsight's 20/20 when you look back. When I look back at that 40 years of learning, and it's pretty been an intense learning, is infrequent data, too sparsely spatial data means that you rely on your mental model a lot, and that's not necessarily true. So we all learn by simple mental model, and there's nothing wrong with starting with a simple model. It's not listening to when the other data arrives. So what I see with high fidelity pressure data and acoustics for that matter is that it tells us a lot about the nature of those fracture systems in shale. Flow in most fracture systems are controlled by, and this is especially true for unconventionals, by fractures, faults, and baffling. So we didn't talk a lot about baffling. We'll talk about baffling later in some of the other discussions. And fracture systems are inherently complex. And what DTS, distributed temperature, strain gauges, acoustics and pressure data, as well as rate data, it tells us data that's timely. It's no good for me to make it do a simulation study 5 years later and tell you, you overcapitalize that. Well, that's irrelevant. Like, you have made nothing in a timely manner. And so the thing that I would say that I've learned the most in 40 years is the first thing you need to do when you're making a forecast is learn humility. Because if you think you're that bang on, all you have to do is try to predict what the stock market is for the next year. And it'll bring you humility, and it's I've definitely learned a lot. Although I probably still need to learn that lesson again.
Well, thank you, Richard. I think that was very enlightening. I always enjoy your talks, have for quite a few years now, and I think you shed some light on the applications of data as it applies in complex or shale environments, and I really appreciate your time. If you, as part of our live webinar, we'll be giving you information on how you can send questions in to Richard based on this topic, and we look forward to having some more discussions with industry experts. Richard, and thank you very much, and to GEO PSI for sponsoring this event. And see you at the next one.
Thanks a lot.